Welcome to this CodeRage 9 session, the Parallel Programming Library Architecture with Alan Bauer, Embarcadero Chief Scientist. Hi, Alan.
Hello.
New in XE7 for Delphi C++ and Rad Studio, and also for Appmethod September 2014 release, is a new Parallel Programming Library, which is available for both the Object Pascal and the C++ language, and works across all the target platforms that we work with. So, Alan, maybe you could give everybody just a few of sort of introductory thoughts about, number one, parallel programming in general, and also a little bit about what was going on and what you were thinking about when you started doing the design and implementation of the library.
Well, it has a bit of a history to it. I've done a lot of work over the years in parallel programming and looking at a lot of the developments going on there. I've actually followed a lot of the different developments of things such as the Silk, the thread building blocks from Intel, and the task parallel library from .NET. And more recently, been looking at the Grand Central Dispatch that Apple released several years ago. And so all of these different technologies, they have slightly different viewpoints. Of all of them, the sort of the task parallel library stuff from .NET felt much more natural to a Delphi-centric view and to how Delphi would typically be done. And so a lot of the parallel programming library was somewhat modeled after some of the .NET idioms and the way that library works.
But we've had things like asynchronous programming, right? We've had multi-threaded application development. We've had early chips that only had one processor, so what can you do? How does this relate to the world of parallel programming and the library?
Well, what is, as many people know, is that rarely do you buy a computing platform these days that consists of a single CPU core. Even the phone that's sitting in your pocket typically is going to have at least 2 cores on it, sometimes even more. The tablet or the phone-sized tablets and everything, they typically are going to have multiple cores. Desktops, you can't hardly find a desktop that has anything less than 2 cores these days. Even years ago, when they started predicting all of this, at the rise of the multi-cores, people are going to want to start taking advantage of them. We've had things like multi-threading and asynchronous type concepts in the past, but the thing is that threading and parallel are not necessarily the same thing. Parallel is really about utilizing the CPU core in the most efficient, or cores, in the most efficient manner. Threading is about breaking up bits of work into separate threads of execution. Now, parallel is typically implemented using threads under the hood, mainly because the operating system is the one scheduling these threads onto the different cores and then running them simultaneously. Parallel is more related to threading in the sense that threading is used as a way of getting to parallel. If you're not on a multiple core machine, nothing really occurs in parallel at that point. You still have to slice things up and then schedule them onto the same core over time.
Sometimes I think about, in this modern world of graphic processing units, GPUs, what's my favorite one? The NVIDIA Tesla card. You can get them in different sizes, 1,024 GPUs, even more GPUs on a card. Some people use that for graphics, of course, and really great games, but there's this whole world of GPU computing. The parallel you're talking about here is not GPU computing, right?
Correct. Yeah, we're talking about the actual general purpose CPU, the main CPU core that the operating system uses to actually execute itself and to execute user programs. And so we're scheduling onto the CPU, the general purpose CPU in the system. The GPU itself, those are highly tailored for computational, massively parallel computational tasks, in which graphics are massively computational and parallelized. But they're much more tailored for those types of operations. Now, of course, people are using the GPU for general purpose computing and taking slices of functionality and pushing them into the GPU. This library doesn't currently approach that at all, and it is something that we've looked at and have been considering, looking at some of the OpenCL things and the open graphics things to be able to push those kinds of things there. But it's a different programming model, even from normal parallel programming that we're doing on the CPU. but it's an interesting thing to look at.
And I know there's other systems like OpenMP. There's other libraries that people have had for multiprocessing. Those still exist in their worlds and on their platforms as well, right? Whether it's Linux or Unix or other places.
Yeah, correct. Our library is just that. It's a library. There's no core language integration at this point. Part of the reason for doing that is we want to get the library itself and the core mechanics for the library across the different platforms nailed down before we start committing to specific semantics that the language may want to inflict on that or do that. And if you start making mistakes at that point or start wanting to shift things around because you want to say that this is a better solution, you can't really change semantics of how the language itself works, but you can change semantics of how a library works and evolve that much more readily than you can trying to change syntax of a for loop within the language itself to introduce new semantics because you can't affect the old semantic. It's actually much more limiting by having a language integration. It sounds great on paper, and a lot of things are doing it. Like you have Silk is doing that. The OpenMP stuff is language integration things. They're focused more on very small pieces of what we consider parallel programming itself. I'm looking at much more broader uses of the parallel programming, introducing asynchronous programming better into the language or better into the libraries, in addition to doing general computational tasks in parallel as well.
Is there any magic tool that you have, Alan, that will take my code and parallelize it for me?
Unfortunately, the panacea of the make my program faster switch just doesn't exist. There's been a lot of research in this area, both in academia and in the industry itself. I mean, I follow some of the guys out of Microsoft that do a lot of this and out of Microsoft Research. They've yet to find the magic pixie dust that they can just sprinkle over your program and it makes it, suddenly figures out where to make things parallel and all of a sudden it works.
So maybe then we'll switch over to the parallel programming library that you've implemented and that is part of, again, the latest releases of our products. As you mentioned, there's this new unit with the interfaces in Object Pascal and C++ as well with the system threading namespace. In Object Pascal, the unit namescope system.threading. It's the same library with the same capabilities on all four platforms we support, Windows, Mac, iOS, and Android?
Correct. If you look inside what we ship, I don't believe there's any if-defs whatsoever in the code, even in the implementation between the different platforms.
Okay.
So it's built on top of all of the low-level cross-platform functionality that we've already introduced into the libraries and into the tools at this point. And so there's no need for any kind of if-defs or uniqueness across the various platforms because it's actually built on top of, like I said, it's built on top of the T-thread is there. It's built on top of any kind of synchronization or things like that. It's all based on some of the core synchronization objects that we've added over the years. There's no need for having a different implementation or having something. So you can be fairly assured that you're going to get same semantics across your different platforms. The only differences may be in terms of how the threading model on a given platform, how the OS schedules threads, may be a little different depending on the platform. And yeah, I mean, when you start using the library and as you start scheduling more work into all the different cores, other things start happening that you typically don't think about, but you have to start thinking about in terms of power dissipation and battery life and things like that. So as you light up more cores, it takes more energy. You got more transistors switching inside the CPU. It starts burning more juice. And so, if you're going to run a long-running parallel process on your quad-core phone, don't expect great battery life.
So getting back to, I mentioned earlier that I was looking for this magic tool that would, in a sense, parallelize my applications. But if I look at the implementation of the parallel programming library, you're giving me some hints in how it's implemented. There's a parallel for loop. So if I've got for loops in my application, I can start thinking, gee, I wonder if I could parallel parts of the insides of those. Correct.
Yeah. The idea is that you can look for opportunities to put things into parallel, especially if you're doing computational type operations over an array of things, matrix type things, or even what if you're going to process a bitmap that's maybe you want to do that on the CPU, you want to do some sort of an effect on that on there, and so it's an array, and so each individual cell can be considered individual, and so you could actually break it apart fairly easily, make that parallel. When you're doing things in parallel, you still have to deal with synchronization and other types of things, but you got to be careful about that, because as soon as you start introducing synchronization objects into your parallel loops, you actually start destroying the parallel nature of things, because as you block operations on a given computation, waiting for something else to happen, that thread can't be doing anything else at that point. So it's blocked, waiting, and so that core suddenly is going to be scheduled off doing something for some other program and not yours, and so it's not going to be able to as effectively use the cores as it could. You have to look at your data more than you do about your actual program and the actual statements that you have, but you have to look at the data. Can the data be done in parallel? And so the prime example, I wrote, that's one of the first examples, which is just a simple example of Conway's life, which is just a grid, and then based on the current status of the grid, that determines what the next generation of that grid is going to be. And so while the source grid is static, the new destination grid is what I'm constructing, but I'm actually constructing each individual cell based on the previous generation independently of all the other cells. So there's no dependencies across any of the different loops. So you can actually schedule all of those things and parallelize the generations, the generation calculations of for the Conway's life. So each cell can be determined from its previous generation independently.
And I know some of the other examples we've done things like finding the prime numbers between
Correct.
0 and choose your favorite highest number. Those calculations can be parallelized and thrown out to the different processors.
Correct. Yeah. So little things like that are very eminently parallelizable. You can't really make blanket statements as to this is parallelizable, not, because there's so many different things that you can rearrange how you approach the problem in a way that makes it even more parallelizable. So it's really going to be up to other people, the users or the developers, to actually decide how to do that. And I would really encourage people to start reading up on not only just threading, but also on parallel processing and library, things like memory models and concurrency and things like that. So there's a lot of little subtle things you have to be aware of. And most of the stuff that's in the library and the operating systems kind of shield you a little bit from some of the real niggling, low-level stuff, but you still have to be aware of them.
In the prime number generator, I had a global variable that was counting the number of primes being found. So I needed to make sure I was synchronized properly when I was going to increment that global count across all the different
Correct. Yeah,
parallel
you do need
fours.
to. There's different granularities of locking, and so when a lot of people, they think of critical sections or mutexes as being this, as being a sort of the smallest granular thing, but you actually have much even smaller than that, where you can run. Most processors allow some level of atomicity for operations, and so on small slices of data, and so like an integer can be incremented atomically, which means that no other parallel core can be also incrementing that value until it is done incrementing. And so when the next core wants to try and increment it, has to actually stall that core slightly to increment it as well. Some processors, like the Intel processor, as long as you're aligned properly in memory, a increment instruction is going to be atomic, but you're not guaranteed atomicity because you're not necessarily guaranteed the alignment. Other processors do different kinds of things. ARM, for instance, has a different mechanism for guaranteeing atomicity, and it's actually a multiple instruction thing rather than just being a simple modification of an existing instruction like on the Intel to implement a synchronized increment, whereas the ARM, it's a little bit more complicated.
Or maybe user interface, I'm updating some edit box or some UI element of a VCL app or a FireMonkey app. In that case, if the different cores want to go at the same areas, we'd want to synchronize something, right?
Correct, yeah. And typically, though, what I would recommend is that from within your parallel loops or the task or whatever you're doing, if it's just a standalone task that you want to schedule into the thread pool itself, or you have a future, and we can talk a little bit more about those, but in terms of just doing loops like parallel for loops, in general, you want to complete that task before you start really notifying anything. Because as soon as you start trying to notify other other outside things, you have to introduce some major synchronization things, especially if you want to synchronize against the UI thread. And so in that case, it literally has to block waiting for that to occur. Now you can queue events in there and it won't necessarily block, but there's still a little bit of overhead in just queuing up an event into the global synchronization queue. If, for instance, the game of life thing that I wrote does no updates until it's actually calculated a generation, whatever big the board size is and the world that you're calculating, it doesn't do any kind of synchronization or any kind of notification as it's working until it's done. Well, the idea is that it's going to happen much, much quicker, so you don't need to really keep the status update during the middle of that time.
We'll come back to Parallel 4 in a moment, but I wanted to make sure we talk about the two other major areas in the parallel programming library, tasks and futures. And future is related to tasks, right? So maybe tell people a little about what a task is, what an interface to a task is, and then what a future is and how it relates.
We start from sort of the low level. The first thing that the library introduces is the notion of a thread pool, which is just a general purpose thread pool, and you can actually schedule work into the thread pool independently of tasks or anything like that. So you can schedule work into the thread pool. And the thread pool is self-tuning. It figures out how many cores you have. It will, based on the load on the CPU, it'll actually add threads if it needs to. So say you've scheduled a task into the thread pool and it's taking a long time to run, or maybe it's blocked waiting on something. So it may actually decide that I need to add a thread into the thread pool because I'm not really utilizing the CPU as well as I could because some other thread is currently being blocked. And as the CPU usage then goes up above a certain point, it'll start aggressively trying to retire threads as well. And so it'll shuffle the work off from a retired thread back into other queues within the thread pool, and then they'll start taking over that work as well to try and not oversubscribe the CPU. So if you've got 2 cores, you don't want to run 100 threads that are all actively doing something because just the thread switching overhead will destroy any kind of performance improvements that you have. So it's better to actually, if you're going to serialize stuff, it's better for the user's program to serialize that and break it up based on how many cores it has than the CPU to try and do that. It can't easily figure that stuff. You break it up into small enough pieces in your various tasks and bits, it can more efficiently schedule across the different cores.
What is a task?
A task is a unit of work.
Okay.
So if you just think of a task as just it's something that you need to get done, and generally it's going to be independent. You don't care what thread it's on. You don't care what core it's executing on. You just need this work to be done. Now, knowing that it's going to be executing possibly on a thread that isn't the thread that you actually are currently executing on, either the main thread or whatever, whatever task it is, it needs to also be aware of the fact that it's going to be executing potentially on another thread. It could still actually execute on the current thread as well, but it's up to the thread pool and the task itself to figure out how to schedule things into the thread pool. So you still have all of the normal traditional constraints of threading, but the task allows you to break things up, and then it will schedule into the thread pool. You don't have to worry about creating threads. You don't have to worry about managing your threads. So you can just create the task. It'll run a certain bit of functionality, and then the task can be completed, and you can wait for it, or you can wait for it to finish.
So it's an object. It's a class.
It's a class, but you really interact with most of the things in the task portions of the library through these interfaces. You'll request that a task be created with a given bit of work, and it's going to return in this interface or an iTask interface. Okay. And so on that, you can actually wait for the task to complete, or you just can hold on to it, or you don't have to hold on to it at all, and it'll eventually just finish itself, and it'll go away and clean up itself. So the idea is that either you can hold on to the task, or you don't have to hold on to the task. And being an interface, it allows that flexibility. The same for things like the future. You don't actually create the future objects yourself. You let the thing and it returns a future. And a future is slightly different from a task, to where, say you need to calculate some value, or you need to run some query, or you need to operate on something. But meanwhile, while that's working, you want to do some other calculations, and so you don't necessarily need the result right away, but you know at some later time you're going to need this result. And so you can schedule a future, which it's a generic interface, and so you schedule it based on the type of the thing you want to calculate and return. You provide it with a function or a method that actually does that calculation, and that's what's scheduled as a task. And then once it's done, it returns the result, and then you can request the result. If the result's not available by the time you request it, it will block waiting for the result to be available.
So that's done under the covers. I don't have to issue some wait command or some sit there in some polling.
No, you just say, I need to get my value now because I need it now, and if it's not completed, you'll block waiting for it. Now, you can ask to see if it's done and keep going if you want, or you can poll it if you want to. That's all possible. Or you can even block waiting for the thing to complete. So, because a future is really just a derivative of a task. Okay. It just has specific functionality.
So in tasks, when they get started, the tasks are started. Maybe I create an array of interfaces for tasks, and I start a bunch of tasks, go off and run some functions. What choices do I have to either wait for? Like, I need all those tasks to complete so I can move on. I can do something.
There's functions that allow you to pass that array in. You can ask to say, return when any of these tasks complete, or return when all of the tasks complete. It's sort of a wait for multiple kinds of a thing. And so you can wait for any of them, you can wait for all of them. If you wait for any of them, it'll tell you which one, the first one it figured out that completed. And if you're waiting for it and it got completed before you even finish the wait, it'll immediately return on a wait for any, and a wait for all, and a wait for all of them.
So when I have an array of tasks, does each task have some status field somewhere so I can see which tasks are done? Maybe I want to update the percentage of tasks completed as a user interface or something. Can I?
Yeah, you can query the state of the task. Is it being completed? Is it even pending? It could not even have been scheduled yet into the thread pool because so many other tasks are going on, and it could just be there waiting to be scheduled or waiting to actually be run. It's sitting in a queue somewhere and ready to go.
In all these cases, the parallel for loop, the tasks, the futures, are those the three major parts that an application developer might use, or are there other parts of the parallel programming library?
Those are the major portions of it. There's the idea is to provide as simple of a sort of a design that gives you a lot of power with very little confusion and stuff. Lots of different little things. So, but even then, there's a lot of little options you can do. For instance, the parallel loop, you can actually iterate over various ranges of things, and also control the loop itself like you would typically control. So you could, suppose you decide you need to terminate early, so you can actually get a sort of this loop status or internal loop status that gets passed to your looping function. In addition to what the current index you need to process is, you can actually tell it, I need to cancel or break out of this loop, which is an interesting problem because you have other threads are also running other iterations and things, and so they may need to either complete or finish up somehow, but then once control is returned, it's going to go back through the next iteration of whatever thread is actually executed, whatever portion of that process is done. And if one of them decides I needed to break out of this loop, it'll return to you as a sort of a result that will say I was able to execute. This is the highest index I was able to execute. That doesn't mean that every index between the lowest starting and that highest iteration actually did run. It just means that this is the highest one, because it could interleave across the whole range in different ways depending on how things are scheduled.
So parallel for, if I remember correctly, I remember when I was in the ID and I tparallel.for and then I put left parenthesis, a whole bunch of choices come up. But I think the common ones are there's probably the first 4 parameters, maybe. There's
a lot of overloads depending upon how you want to actually run the thing, and so you typically give it the low bound and the high bound, and it's modeled after a normal Delphi for loop, which is it's low inclusive and high inclusive. You go from the low value to the high value, and then there's what's called a stride, and a stride is more or less a way of pre-tuning the for loop. If you have a fairly small set of iterations you need to do, you probably want to pick a smaller stride. You actually don't need to even really worry about that. In general, you want to only use the stride if you've got a large number of things and you want to pick a larger stride out of the gate so you get better disbursement across your work process and everything. So if you're doing a parallel for loop over, say, 100 items, you may not really need a stride of more than 4 or 5. So what it does is it breaks it up, and the stride is how far apart from each iteration does each thread get scheduled. The farther apart they are, in general, that keeps for a lot of different cores, that keeps the different CPUs sort of from stepping on each other, because a lot of times the data is going to be physically in memory located next to each other. And so by having a different stride, you can actually improve performance, because the different CPUs they're accessing different portions of the cache on the CPU, and so they don't end up with implicit inherent cache locks and cache line locks at that point. The stride is more or less sort of self-tuning as well. So if you start with a low stride, you just pick one at the start. For loops that have just, say, 10 iterations, it'll actually schedule as many as it can up to the number of cores that you have. So say you have 8 cores and you have 10 iterations. It may actually schedule 8 of those iterations simultaneously into the thread pool and then execute them virtually all in parallel. Whereas if you had picked a stride of much higher than the actual range that you have, it may only schedule a couple of different processes or different tasks to work across your entire loop, and it may actually be worse performance at that point. In general, if you let it tune itself, you're probably okay, because what it does is it tries to the first time through, it figures out that I'm going to try close together, because you may break out early or whatever, so I'm going to get as many scheduled as possible iterations, and then it'll actually lengthen the stride as it runs the process. So it'll lengthen up to probably about 128.
So what I wanted to do, Alan, is just bring up the ID real quick, and again, this session is for both, is in some ways language agnostic, but I'm going to bring up a Pascal example that has a for loop and a parallel for loop. This is the prime number example, just so we can see that here in the button click, we're just running through a for loop from 1 to some maximum and asking by calculating, is that number a prime number? And then incrementing this total number of primes found, and it's using the stopwatch object to calculate the time. And then over here on parallel for, here we say tParallel.for, and then we have several parameters. This is parameter insight on a parallel for. What are some of these options here that we're seeing on the screen?
Well, the biggest one is that you can pick either a regular integer or 32-bit integer range, or you can go to a full 64-bit integer range and stuff. So typically you're not going to, the integer range one is going to be the most commonly used one, so you can probably cut half of those overloads out. The other one is that you can see that there's different ones that take anonymous methods that you can call directly from Delphi, and the code that you're showing here clearly demonstrates the use of the anonymous methods. The other one is that if you just use normal method pointers, and from C++, you would typically use regular events because they're both supported on both as well, and anonymous methods aren't as easy to do there. So various different types of loop or iteration functions. Some of them take loop state, and that's what I was explaining before, is if you wanted to actually control the loop, if it needs to exit early, you can control where you're at and stuff like that. So you can still do essentially what is a break at that point. So if you need to break out of the loop, you can also determine if some other loop iteration has maybe raised an exception at that point. So you can determine that, or if for some reason one of the other loops decides it needs to cancel, and so you can tell whether or not one of the other iterations is either broken out or is requested some sort of a cancellation. So you can, in your own code, test that. If you got a longer running process, you can periodically check that value to go, oh, somebody's requested a cancel, and then immediately return at that point.
So I see here low inclusive, high inclusive. That's the range of the for. And then I see an iterator event as an example parameter.
That's the actual event that gets called per iteration. And you'll get passed in at least the index, the current index that this particular iteration needs to process.
So I can get the loop state. I can see what the current index value is.
Correct.
I want to stop or something.
Right. Then if you want to, like I said, you want to control the loop, you can break at that point. Okay. Or you can determine if something else is happening, or somebody's requested cancellation, or there's an exception that occurred in some other iteration.
And then I see a thread pool
Yeah, the thread pool, there's a global thread pool, and in general, you're not gonna want to create another thread pool, although you can actually instantiate another thread pool, and then you can pass that thread pool in. You can actually take the thread pools. They have some tuning parameters in terms of the maximum threads they'll create. They'll still both try and load balance based on the number of how much CPU load is occurring. But it will, you could, for instance, decide I want to schedule half of my cores into one thread pool and another half into another thread pool, and then independently schedule things into them based on maybe two different sections of your application. You want to keep them independent. Again, those are all scenarios that are going to be based purely on the developer's decision, what they think is going to be best for their application. In general, I would say that clearly the 80 to 90% case, the default global thread pool should be sufficient.
Now, I know that in a regular for loop, if I choose to, I can choose to either break it or exit from it, right?
Right.
And that's
what the loop state is for. So if you needed to break out of the loop, that's how you would do that. Now, because you're actually executing each individual portion of the loop, you're not technically in a language for loop. So things like exit is just going to exit out of that current iteration because it's just a function call. Break would just, if you're not in a loop within your loop, your iterator, that's not going to do anything for you. Continue doesn't really mean anything. So in those sense, continue is just you return from the iterator and then it just goes to the next one. Break, you have to actually tell the loop state you have to use the one with the loop state, and you just tell the loop state dot break, and you say I need to break, and then you return at that point, and you just exit, and then exit. You can't really, if you have code in there where you run through a loop and you exit out of your function completely out from within the loop, you have to do some things a little different. So you have to then break the loop as quickly as possible, and then just return, and then it'll still come out of that. So some of the more languagey stuff there's really no direct analogs. You got to do a little bit more work, but it shouldn't be difficult for people to figure out.
And again, if I've got a bunch of things running, can I cancel them all? Is there some call that I can say cancel everything that's running? I need to go do something else.
Right now, there's no cancel lots of things at once. Right now, that's one of sort of the future kind of things we're looking at is introduction of what's called a cancellation token, which you can then pass around this cancellation token to various tasks, and they'll all be looking at this one cancellation token. So you can hold on to it, and you can say, anybody that has this token, that has a reference to this token, I want it, and then I can tell the token that didn't cancel, and then everything will then cancel at that point. Now, the for loop stuff sort of has an implicit cancellation in shared cancellation status in there, like at the break. If you want to break out, that will try and cancel as quickly as possible all the other iterations. If an exception gets raised within an iteration, it gets caught, but it also signals that you need to terminate all the rest of the iterations that are currently going on, and it will then you have from the parallel for function there is a loop result structure that you can then get that loop result structure, and in that can tell you what happened. So was there an exception or something like that? In some cases, if there was an exception or multiple exceptions, they'll get aggregated together, and then before the for loop actually returns, it'll actually raise sort of this aggregated exception on the calling thread, the one that actually initiated it, as if the exception had occurred within a non-parallel for loop. So exceptions are kind of a tricky situation because each individual thread has to catch them, and then we have to hold them and then aggregate them, switch them over to, put them into an aggregated exception and then raise that exception. And then you can figure out from there what happened.
Okay, and again, this was the Pascal code for the prime number sample. It's got the from 1 to the max, and then it's using an anonymous method here to call, and then it's using tinterlocked.increment to bump the number of primes found. Yeah,
that's an atomic increment function itself. So that's been there for quite a while. That's in the synchronization objects
in sync objects.
Yeah, so that's been there for quite a while. The Delphi language itself supports across all platforms now. Supports a lot of intrinsic functions that are atomic increment and stuff, and a lot of these the T-interlock stuff is implemented that way, using just the intrinsic atomic increment stuff.
And this was code that just creates a task and has an anonymous method, runs for a period of time, starts the task. And then I guess here's this wait for all, right?
Correct, yeah.
Or wait for any, I guess was the other option there.
Mm-hmm.
Okay. And then there's another one in this example for a future that just says task future and whatever that type is that.
Yeah, that'll be the result type. In there is the integer. And then it returns a future that has an integer as the instantiated type.
And then, Alan, I wanted to bring up, this is one of the samples you built, which is the Conway's life simulation. And this is the C++ version. So here, inside of your life engine, you called it, there's a parallel 4, and here we're passing the low and the high, and then you have an iterator event. Here's the iterator event. Just takes a sender, and there you're passing in the index. Right.
And then it just calls the process.
And then it calls process cells. Okay. Yeah. So again, under the covers, it's the same, as we mentioned, it's the same implementation, same source code, compiled, the libraries compiled for each of the platforms.
Correct. We don't do anything that right now that is specific to a given platform, unless that platform only has a specific functionality we're trying to expose. In general, everything is done in a way that we're going to try and get it to work on all of them.
And again, you mentioned that the operating system's pretty reasonable about what's going on as far as scheduling cores.
That's a problem that's long been solved by the operating system, and so we might as well just let them, deal with that. And besides, in where our applications run in sort of the user space, we don't really have that level of control of how we schedule onto what CPU. Windows, you actually kind of do, because you can actually set CPU core affinity on a thread and things like that. But I'd be very cautious about doing that kind of stuff, especially within a thread pool thread. If you say, I only want this thread pool thread to be scheduled on this particular core, within that thread, you can really mess with stuff at that point.
And again, the thread pool self-tuning and the major features are the parallel 4, the task, and the future.
We'll look at, adding some more types of things in the future, adding more support for trying to parallelize other types of operations and things like, a common one would be enumerators.
Alan has done the Conway's Game of Life, which was from Scientific American.
I just picked something that I knew was going to be very graphical and very parallelizable at that point. And it would be something that it was large enough grained in things to where, and it was something that almost everyone has encountered in their early computer science, or even a lot of people. I've figured it out back when I was even in high school and before. I've seen that particular type of programming.
And if you have our products both into samples, which is the user public documents, Embarcadero Studio 15 samples, under Object Pascal RTL, you'll see parallel library, and then you'll see a FireMonkey version and a VCL version. And then the shared code is the life engine code itself. Right,
the life engine itself that does the actual parallel processing and stuff, and that compiles for all the different platforms. Again, I segregated all of the UI bits into the different, the FireMonkey and the Delphi version, and then the actual life engine that does the generational calculation of Conway's life is in the shared code, and that unit compiles on all the platforms unchanged.
And then you've got a bunch of the sample life files for starting points.
Yeah, I found those. If you look at Conway's life and you Google through that stuff, there's a whole bunch of resources on that. In fact, there's sort of this subculture I found within the Conway's life, to where they're trying to find what is the most prolific and the smallest pattern that creates the most prolific thing. And actually the one that's there is the acorn.lif is sort of the one that produces the most prolific patterns from the smallest starting pattern.
And there's C++ versions. There's the life engine in C++. Again, it's in the user public documents, Embarcadero Studio, CPP, RTL, parallel library. Again, VCL and FireMonkey versions of the C++ samples. So any other last comments or thoughts?
Yeah, I would just recommend, there's a lot of resources available that really talk about concurrent programming and those things. There's a lot of stuff coming out of MIT labs that discusses that. And then a lot of stuff out of Microsoft Research did as well. I believe there's some Carnegie Mellon resources as well, some white papers in there. One of my favorite books is one written by Joe Duffy from Microsoft. They did the actual task parallel library for .NET, his team and everything, and he wrote a book called Concurrent Programming on Windows. It's a very thick tome. Don't be afraid of the fact that it says Windows, because there's huge amounts of information there that are completely agnostic to Windows itself. There's a lot of Windows isms and stuff, but it talks about C++ parallelism, it talks about .NET parallelism, some of the resources for just the general Windows APIs, but it also goes into general concurrency concepts in dealing with how you can actually reason out whether or not a particular set of instructions can be run in parallel, and so what kind of weirdness can occur when you have two threads executing through the same bit of code without either with or without proper synchronization, or do you care about synchronization or not? Because there's some cases where you may not even worry about it and think it'll still be correct. Other cases you do need to worry about synchronization. There's a lot of stuff out there, but I would really recommend really kind of learning about not just threading. Threading is very important in synchronization across threads and when you need to synchronize, how things actually work. But in parallel programming, you also have to look at how you can structure your data in a way that is as most parallel as possible, so you can get as much benefit from that. And a lot of times that requires as little amount of synchronization as possible in order to gain the best performance. So that's why each iteration needs to be as wholly independent, that you can't have any dependencies across the different iterations, and so you get maximum benefit from actually going parallel.
It's your time now with Alan Bauer, so it's time for Q&A. You can put your questions into the Q&A log and go to webinar, and we'll take a look at the questions you come up with and see if we can answer them. Alan, Carl has a question here. He was mentioning that Boost has a future implementation and C++11 has in the Language Center futures. And how does this relate to the futures that are in the parallel programming library or not?
They're wholly independent of one another. So because this library was designed, as first of all, is to be completely cross-platform, and also the cross-language library. It's also written using Delphi and Object Pascal, so it can be used both through both of them. So the stuff they're working on with the Boost libraries and the C++11 features and things, they're largely independent. Now, we certainly look at how we can get the two to cooperate with each other. That's something we can certainly do.
And I know it was interesting for those of you that were with us earlier with Bjarne Stustrup he did his presentation, then we had some Q&A, and one of the questions came up, and he was also talking during his presentation about how they were prototyping some of the capabilities using libraries before they ever thought about the requirements maybe of adding to the language. And I had to smile because when we were having our conversation last Friday, you talked about the same thing. Would you like to sort of recap again your thoughts about here, we're doing this in the library, but there might be future opportunities in language syntax.
Certainly, yeah. The question always inevitably comes up, asking, how is this going to integrate with the language? And really, what we look at doing is to, like Bjarne actually said, is that you want to prototype some of the designs and the layout of the underlying functionality prior to even thinking about how that would actually integrate into the language. Once you've integrated into the language and whatever semantic that you've chosen for the language, either both syntactically and semantically in the language, you tend to be locked into that. And without some way of just prototyping that and getting the underlying functionality the way you like it, first get all that done first, then you can start thinking about how to get it integrated into the language. And that allows you to evolve the framework in a manner that more or less follows whatever architecture and industry standards or any other things that are coming up throughout the development of those libraries. So you can make sure that you're getting the right implementation, the right semantics for what you need.
I'm trying to type as we go along as well. Yeah. And Carl's just making a suggestion, maybe it's for you, but also for the next session with Bruno, about maybe a best practices blog or articles and documentation about how when something is implemented in C++ and you want to use it in Delphi, or something is implemented in Delphi, how to use it in C++.
Certainly, yeah. That's a much more generally useful thing to have, and that's something I guess Bruno will be discussing coming up in the next session. And as always, we're trying to always continuously improve the documentation, improve that. Suggestions like this about where people are struggling, where they liked us to focus some of our efforts. That's great to have that kind of feedback. So.
And I also know that if you look at the documentation, the doc wiki, in a lot of cases, we will show you the Object Pascal or Delphi definitions and interfaces, and right below it the C++ interfaces as well, or the uses. And in the tutorials now in the doc wiki for the examples, we're trying to have 2 columns where we do it in Delphi and in C++ Builder for the implementation of parts. So I know some of that isn't all complete, but again, the whole team is trying to make sure, especially when it's the frameworks, for example, and the shared framework, FireMonkey, the shared RTL. And again, Bruno in the next session is going to talk more about some of the I'm always trying to avoid talking about things that have language connotation, the aspects or the intents or the concepts that are behind some of the work that's being done.
Yeah, those aren't language terms at all by any.
We're going to throw those out. And I know we talked about, in this case of parallel programming, earlier today, someone, and I was meaning to write a note, but it's in the total Q&A log, about is there a future for your thinking about the parallel programming library as it relates to distributed parallel programming? You know, if you were going to take parts of your application, put it on different computers, on different servers, and so on.
Currently, no. The library is designed for more local, multi-core, general-purpose CPU usage. We have looked at and have looked at what it would take somewhat to do similar things like that, or GPU usage, OpenCL, CUDA, some of those other libraries. But those not necessarily being general-purpose, CPUs, they're much more focused on their specific tasks. So not that they're not useful for a lot of things that you could consider general purpose, but for this particular library, its effort was focused on just multi-core, things, and also the cross-platform aspect of it. The whole library is built in a manner that it builds for all the different platforms we support, and also upcoming platforms that we're looking at as well.
I'm trying to make sure, because these microphones have different levels on them, and they're different mics. But now if you're doing heavy parallel programming and running all the cores, I don't know what you've got there, but I've got like an iPad and an iPhone 6 now. These things can get hot if you're doing a lot, right?
Of course, yeah. You light up, you start switching more transistors on those CPUs. It's going to take more energy, and don't expect your battery life to be as well as it could be. But it's certainly possible to do on the mobile. In small, short bursts, you can actually do things fairly efficiently at that point.
And it looks like Carl has put in a suggestion about what about a library for certain. Now that we have the parallel programming library underpinnings, what about a library of some concurrent or parallel algorithms and for array handling and so on? It might be that we could build up some sample libraries of higher level constructs and structures.
Right, building on the current parallel library, looking at how we can leverage that for some higher level constructs like arrays and matrices and things like that. A lot of those, they could just be done either through demos and stuff, because it's very difficult to come up with something that's general purpose enough that people can use on a wide enough range of things to really justify a lot of effort put into that. But of course, there's certainly something we can look at doing there. And the more that the library gets acceptance within the community and everything, I'm sure that other people will start trying to leverage that and start presenting, either through some open source or their own examples, or putting that stuff out there as well.
Yeah, I know I did I'll have to. I was trying to find it the other day. It's a matrix multiplication example that I cloned from a C# version of the same thing,
Right.
where I parallelized the for loop for the rows, but then left the columns in a two-dimensional way. I think I ran it at 5,000 by 5. I even tried 20,000 rows and 20,000 columns. It worked in Win64. I mean, it was okay,
Sure.
you know.
Yeah.
And again, I parallelized the row processing and then left the columns to do their thing sequentially.
Right.
Yeah. So there's always. Let's see. And there was another thing which, and maybe you can explain it. Maybe Bruno will explain it. I'm not sure, but I was looking at futures and how they're implemented in the parallel programming library, and we were trying to figure out, without a whole bunch of convoluted stuff you wouldn't want to look at, but that we could bury under the covers. And Bruno's going to talk some about how to use lambdas and variadic templates for things that we would use in Delphi with anonymous methods, for example, so you can do things right in line,
Right.
Inside the parallel fours and so on, and such. So I don't know if you want to talk a little more. I know I ran into something in the demo that I did yesterday morning as it related to the futures in the parallel library.
Right. Yeah. There a lot of the library, all the library is written in Object Pascal, and it does take advantage of some of the language features that are Object Pascal generics and things. In the future itself, the future method isn't actually a generic method, in which then returns the generic or the parameter on for the method itself is the result type. And so that does tend to present an issue with C++ being able to use it directly. Again, Bruno will probably be able to present some ideas and some things on how you can actually leverage that from C++ a little bit easier. And in the future, we'll look at how we can better present that to the C++ side as well.
Yeah, so that's for everyone. If you didn't see my 5 o'clock a.m. session yesterday morning, I showed Parallel 4 and I showed tasks in C++. And I'll get that source code out there for everybody, and the replay will get put up if you missed that one yesterday. And then we'll come up with, and Bruno again is going to show some stuff here at the top of the hour. So if you have any other questions for Alan, put them in. Alan, do you have anything else to add on this whole discussion about the library, the architecture, and maybe future directions?
Well, when I did the session for the Delphi side of things, a couple of questions people had asked. A lot of them were asking about how you deal with synchronization and how you deal with updating a UI and things. And a lot of that was they're just asking that, is there something different about this? And so, what I tried to express, and part of the presentation also expressed the fact that a parallel library is implemented using the threading underneath it that the operating system provides, because that's actually where the scheduling on the cores occur. And so threading is how the parallelization is done. Because of that, the actual all the rules about multi-threading and synchronization still apply. So when you are running in a parallel for loop, the actual loop iterator function or the anonymous method or the lambda or whatever you're using for that will be executing concurrently on however many cores that you have. And so because of that, you still have to deal with all synchronization and things. I also mentioned that you still need to be somewhat careful about doing those synchronizations, because you can quickly destroy any kind of parallelism that you've done by starting to introduce synchronization objects or synchronizations or locks within the looping itself. And so the idea of the parallelism is to leverage as much of your cores to get as much work done in as short a period of time as possible. And so as soon as you start trying to synchronize things, even something as simple as posting a message into the message queue can sometimes create a lock, at least on Windows, that could potentially serialize things when you didn't, and actually hurt performance. So but that doesn't mean that you can't do those kinds of things. I'm warning against that you may end up hindering your performance at that point. So,
as well as in our conversation, you talked about if you throw too much at the cores and too many threads and so on, you could spend all your time dealing with overhead versus getting actual work done.
Correct. Yeah, you do need to structure have your data structures arranged in a way that allow you to get the most maximum effective use of your cores. For instance, you said you did this matrix calculation where you did all the rows in parallel, but you left all the columns serialized. That's actually how the Life engine itself works. It does all the rows in parallel, but then each column is then done serialized. And so, since each column calculation is largely going to be about the same amount of time for doing all of the columns in a given row, it really doesn't make sense to try and parallelize each individual cell within your matrix or your array and everything. So at that point, just parallelizing the various rows in the calculation gives you the maximum benefit without adding too much overhead in just both thread switching and the task management itself within the library itself. So you've got a balance between how much work that you want to break it up in how many different pieces and schedule them into the thread pool and the tasks and everything, with getting the maximum amount of performance.
And I made the mistake when I first did a tasking example. It was not single task, but I would create multiple tasks, and I put a synchronization in the event processing for each task. So the task actually ran and did its thing, but then I had to synchronize for a UI element, and then I had a wait for all in my main. And so the tasks completed, but they were trying to synchronize while I was sitting on a wait for all in the main thread, and so nothing could complete.
Sure, you still have to be careful about deadlocks and live locks and other common pitfalls you can run into with multi-threading. So, all of those same rules apply. It doesn't absolve you from having to think about and deal with those things.
And I seem to remember, I think there was a timeout parameter you could supply. Did I see that or remember that correctly? There was some parameter.
Sure, yeah, all of the blocking and the wait for stuff you can. There's a timeout and everything, so you can have a timeout at that point. And in your particular case, where you're trying to synchronize, you have the main thread sort of blocked, waiting for something to happen, and the synchronize is then waiting for the main thread to actually process things, and so it hasn't returned to the get message or the peak message on Windows or whatever the event loop, so it can actually do the synchronization at that point. So it's a classic deadlock.
And it turned out I didn't need to update the user interface inside of the task. I could update the user interface outside. So I just commented out and did the user interface update outside of each of the tasks. It was not a problem. So
right. Sometimes it's trial and error. You can play with it a little bit and tune things how you like. Try it on different machines with 2 cores, 4 cores, 8 cores, or even single core, and see how your performance scales. And everything. Sometimes just playing with certain parameters and how you break things up you can realize maximum benefit by doing that.
Well, Alan, thank you very much.
All right, no problem.